I was out early this morning and I saw this. Well, it was this enormous orb web strung between two fence posts and covered in dew. It just looked impossible. So fragile, but holding this perfect shape. But that visible simplicity, it turns out, is a profound architectural lie.
It really is. The complexity is hidden in plain sight.
Okay, so that's our mission for this deep dive, to really analyze the geometry of the spiderweb. But first, we have to talk about the material itself. I mean, the stats are just staggering.
Oh, absolutely. Spider silk is, what, roughly 5 times stronger than steel of the same diameter?
5 times, and the stretch is even crazier.
It can stretch up to 400% of its original length before it breaks. It's an unbelievable natural fiber.
So you have this incredible material. The question is, how does the spider arrange it to, maximize all that strength?
And what's fascinating here is that the blueprint is basically universal. The classic orb web combines two very mathematically precise structures.
Okay.
The first are the radial threads. You can think of them like the spokes on a wheel.
Right, the lines going out from the center.
Exactly. Those are the load-bearing cables. They're designed for multi-directional load distribution, so tension is pulled evenly across the whole thing.
And this is where it gets really interesting for me. What about the sticky stuff, the part that actually catches the prey?
That's the spiral thread. And it's not a random coil. Our sources show it often approximates what mathematicians call the logarithmic spiral.
A logarithmic spiral. Why that specific shape? What makes it so efficient?
It all comes down to its trigonometric precision. The spiral keeps a constant angle to the radii as it moves outward.
Okay, what does that mean in practical terms?
It means that no matter where an insect hits the web, the load is distributed almost perfectly back to those strong radial spokes. It balances the most surface area for trapping with the least amount of silk. It's pure economy.
That mathematical rule must be incredibly robust then. Does it work for those giant webs you hear about?
It absolutely does, whether it's a tiny web in your garden or, those massive ones for Madagascan spiders with drag lines 25 meters long.
25 meters, wow.
The fundamental radial spiral geometry is exactly the same. The principles just scale perfectly.
So that's the static math. But what about the physics? I mean, a bumblebee hits that thing at speed. How does it handle that impact without just shredding?
Right, that's a great question, and it moves us into engineering resilience. The web survives because the spider doesn't just hang the silk. It builds the whole thing under tension.
So it's a self-stressing structure.
Precisely. The whole thing is a self-stressing cable net. It's pre-tuned from the moment it's built.
So the spider is like pre-tuning this massive network of guitar strings.
That's a perfect analogy. That pre-stressing is the key to what we call stress harmonization.
Stress harmonization.
Yeah, when a local force hits an insect, a gust of wind, the tension allows that force to be redistributed instantly and smoothly across the entire network. It's designed for damage tolerance, not catastrophic failure.
That kind of sophisticated approach to design, it reminds us of the complex systems we all deal with. If you need help figuring out where next-gen agents or automation could make the most impact for your business, you should check out Embersilk. They handle AI training, automation, integration, all of it. You can find them at embersilk.com for your AI needs. So, thinking about that damage tolerance, what does this all mean for us? For human engineering?
Well, the applications in biomimicry are, frankly, inspiring. In material science, researchers are creating engineered fabrics that mimic that spiderweb orientation.
Or radial spiral layout.
Yep. And they show phenomenal results in burst strength tests. When you apply a sudden force from multiple directions, that natural geometry just blows conventional grids out of the water.
So for things like protective gear or vehicle composites?
The potential is huge. It's about absorbing force from multiple directions at once, just like the web does.
And what about on the really, really small scale? We're talking nanometers, right?
Yes, and that might be the most futuristic application. Scientists are using single silk strands, sometimes just 10 nanometers thick, as a physical template.
A template for what?
They coat the silk in a solution to create tiny, hollow nanotubes. And these microscopic tubes could be used in everything from fiber optics to microfluidics for lab tests.
It's just amazing. The elegance of a simple spider web gives us this robust, transferable architectural paradigm. It really proves that profound strength comes from geometry, not just the material. We're finding these blueprints for lightweight, damage-tolerant structures that could lead anywhere from better materials here on Earth to, who knows, flexible webs in space one day. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.